Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with Austin, who's going to walk us through Llama. Austin, thanks for taking the time.
Thank you, Shafu, for having me on.
Yeah, of course. Austin, why don't you briefly introduce yourself, introduce Llama, and then directly jump into the code and diagrams and stuff?
Yeah, for sure. Yeah, my name's Austin. I'm a co-founder of Llama. At Llama, we got our start doing DAO services. So we worked with a number of the large protocol DAOs, including Aave and Uniswap and Maker and Lido and Balancer and ApeCoin and Nouns. And we did a variety of things for them, a mix of treasury management, data analytics, growth, risk, really whatever needed to be done. And then starting at the beginning of this year, we took all those learnings and turned that into a full stack product. And so what we ended up building is a governance framework, and it's the governance framework we wish we had when we were contributing to DAOs. And so that's what I'm going to walk through today. The frameworks deployed to Ethereum, Arbitrum, Optimism, Base, and Polygon as of the time of this recording, but we expect to deploy to more EVM chains. So yeah, I'll go over the framework, how it works, the code, and how protocols can use it for their on-chain governance and access control needs.
Nice, that's awesome. Yeah, let's. I think a good point to start at is the diagram before we jump into the code.
Yeah, awesome. Cool. Yeah, I can walk through this diagram here. The the way to understand how Llama works is by starting with this Llama factory contract. And so this contract, it's the same across all the chains we deploy to, and it's just a mutable, permissionless, relatively. We'll dive into the code in a bit, but relatively simple contract that basically just has a deploy function, and it's used for anyone to deploy Llama instances. And so the complexity comes into what is a Llama instance, and you can think of a Llama instance like similar if you're familiar with Compound Governor or Open Zeppelin Governor or even multi-sigs. It's architecturally similar, where there's this factory, you deploy your instance, and then you transfer ownership of your protocol to this instance. And so I actually think it's easiest to start with the protocol and work our way backwards. And so if you look all the way to the right, to the governed contracts, you can think of these. They can be any contracts, and the implementation can be anything. It can be something you roll yourself. You could use Soulmate or Open Zeppelin Ownable or really anything of your choosing. The important thing is just that the Llama executor is the owner of the functions that you want to govern. One design decision we made here is we actually, which is maybe a little different than some of the other projects out there, and something like that we were just thought was really important based on our experience was all like this complexity I'm about to get into. Really, everything that happens in the Llama instance, the permissions and the roles and the validation, that all happens behind the scenes. And then all outgoing calls come from this Llama executor. So that means when you transfer ownership, you just have to do that one time. So the integration is really smooth. I know that's always a stressful point when you're changing the owner of a smart contract. It's something you want to do once and kind of not have to think about it again. And so that's the kind of exit point of the Llama instance is this Llama executor contract, which then calls any governed contract. And one other thing to note is, of course, the Llama executor can call anything you want or permission. So in addition to calling functions that it owns, it could also just call general smart contract functions. Maybe you want to do a swap on Uniswap or something like that. And so that's kind of the framework for the Llama instance. Now I could get into the high level of how the Llama instance works. The way the Llama instance works is there's basically three of these main contracts. There's the core, the policy, and the executor. The policy holders are you can think of them as like the stakeholders of the protocol. of the on-chain organization that's using Llama. And so these can include things like a core team, core developers, operations team, uh, the community. It could include service providers. It could include your grants program lead and team, token holders. Really anyone who contributes to the decision making of a protocol. And so that's what we have here, and that's what those are the entities that are coming together in this decentralized way to make decisions. And so the way they do that, they interact with this Llama core contract, and the way they're represented in the protocol in the Llama instance code is through this policy contract. And so the Llama policy contract is non-transferable ERC 721. And it encodes the roles and permissions of the policyholders. And so policyholders, they create actions, they cast approvals and disapprovals, and we'll get into exactly what that means. But if they do that, and then the validation of their roles and permissions happens with this Llama policy contract. And so policyholders, they're interacting with the core. The validation comes from the roles and permissions that are encoded in this NFT contract. And then the kind of like last core part of logic that's important to understand is strategies. And so when permissions are created, strategies are you can think of them as rules for how an action progresses from creation to execution. And so each permission, which we'll also get into this, when we look at the code, this will be a core part, is it's a tuple that contains a target contract, function selector, and a strategy address. And so to give a simple example, let's say the target contract is some sort of grants program account. The function selector is transfer ERC20. Then maybe the strategy will be something like encode rules for an optimistic strategy where the action will automatically execute unless it's vetoed by the grants program reviewer's role or something like that. And so through the mix of strategies, the policy, the core, and then ultimately the executor, those are kind of the main places where policyholders interact with Llama.
Okay, one question. I think it's super interesting how you're using NFTs to basically define policies, right? So one NFT represents, I don't know, I can spend like 300,000 DAI, or I can vote on this, or I can do that, right? This is how the NFT works.
Mm-hmm.
Okay,
Yeah, exactly.
okay, I see.
Yeah, and so the concept here is the traditionally it's not there's a nuanced conversation here, right? Like, so traditionally, like, you think of governance and you just think of pure token voting, right? Where it's like, if you have 10,000 tokens, then you could propose anything, and then one token, one vote. And it's not that doesn't work or that's a bad idea. It's just that we've seen the limitations, and that can be augmented with what we're calling decentralization through access control. And what it is a role-based governance system where, rather than decentralizing your policyholder group strictly through token distribution, you can do it based on roles. So you could have a grants program that could participate in the grants process, but do nothing when it comes to risk. And you could have risk service providers who could update risk parameters, but not choose who gets grants. And so you're actually segmenting parts of the administrative operations of the protocol into these different groups.
Okay, I see. Yeah, that makes a lot of sense. I think the whole concept, anyone who holds the token can vote on anything, is not the greatest.
Yeah, the reason why is interesting. This is something that I think it would have been kind of difficult. I've always been excited about the prospect of DAOs, and I'm actually I think a lot of people in the industry are they're hard on DAOs. They criticize them a lot, and they think they could be a lot better. I think in the past few years, it's pretty amazing what we've seen. I leave my our experience contributing to DAOs really optimistic on the future there. We've seen many instances of billions of dollars in treasuries, hundreds of thousands of token holders, uh, protocols that have hundreds of millions of dollars or billions of dollars in TVL, and this group of decentralized stakeholders coordinating together to make decisions and updating things on the fly and allocating funds and all that sort of stuff. And so it's quite amazing what DAOs have accomplished already. And so in addition to all the good, we've seen some of the bad too, and I think that's natural. And so it's great to see a bunch of teams excited about the future and trying to learn on some of the some of the mistakes made in the past and improve it. And yeah, I think the reason I say this why that role-based governance is important and why it's nuanced is because the the incentive drift that happens in protocols governance is a natural thing when you think about what happens if a service provider if a service provider has tokens delegated to them, and so they can vote on any proposal, and maybe they get their payment from the grants program, then you might be in the situation where it's awkward because the grants program might be asking for a renewal, and maybe you think it's too large, or maybe you think they're not doing a good job, but then it's awkward for you to do your best job as a token delegate because you're worried that if you vote no, then they won't give you the grant that you need to run your business. And so I think just the simple solve there is a system similar to Llama, where you just separate those duties so the service provider doesn't have to participate in that process.
Hmm. No, that makes a lot of sense. I think, we're speed running how to run an organization, right? I still think, in the traditional, if you have a publicly traded company, if you're a shareholder, you cannot influence day-to-day stuff, right? You vote for a board or some executive that's gonna run the business day to day, and I think in most cases that makes sense. So it's good to see that you guys are working on something where you can build something like that, right? Where you can,
Exactly.
yeah, awesome. All right. Should we jump into the implementation?
Yeah, that'd be great.
Nice.
We can. So what I'm gonna do here is walk through the action process from creation to execution.
Okay.
And I think we'll be able to touch on a lot of these concepts along the way.
Nice. Let's do this. Okay. So you said the factory basically. Okay, the factory creates a new core, right? Okay. So
Yeah,
we're gonna leave out the factory because it's very simple, and we're gonna start with the core. Okay.
yeah, I can actually even just since it's so simple, it's 70 lines of code here. I can actually even show um, the deploy function here. Basically we're just setting some immutable variables, over here in the constructor, and then the only external function is this deploy function. It has some basic checks, and then you can see it deploys the Llama instance. And as we showed in that diagram, a Llama instance is the core, the executor, the policy, and then it emits an event that the Llama instance has been created. And so that's the starting out point, and then we can go to the core to actually see once you have your Llama instance, what can you do with it. And so the I can walk through the action life cycle, and like I said, yeah, I think that we'll touch on a lot of these key concepts.
Awesome. Yeah, let's do that.
Cool. So first, starting off, what is an action? You can think of, I think most governance frameworks refer to them as proposals. Actions they're essentially the same thing. We wanted to call them action just to promote this idea that usually you think of a governance proposal. It's a really big effort. You're circulating a document for feedback. You're talking to fellow voters. You're posting on a forum. You're doing a temperature check. We wanted to promote this idea of action should be these really atomic units of work where you can create a lot of them, and using something like Llama, if you divide the responsibilities for approving and disapproving and ultimately executing these actions, then you can actually work together to do a lot more to be more effective as a decentralized group of people who are governing a protocol. And so the if we look here, we see create action, and so this is what you use to actually start off the action process and create an action. This function is simple because we actually have the internal logic here. And the reason we do this, I could actually show you, is because we also have a create action by signature function. So this is just allows meta transactions to also create actions on a policyholder's behalf for, we could do things, some features we could enable with this is in our, off-chain application, we could broadcast, we could offer gasless transactions for creating actions. So if we get into the create action function, we see the crux of an action. It's policy holder. So this is the message sender. They are specifying the role they have, the strategy they're using for the action, the target they're calling, the value. This is just the if they're passing along any ether, the description over here, and then the data. So this includes the function selector and any and all the call data. We do some basic checks right here to make sure the strategy is correct, and then we do a calculation of the permission ID. And so this is what I was talking about before, where the permission is actually it's a tuple. It's the target address. As you can see, we're grabbing the first 4 bytes of the call data, so we're getting the function selector and the strategy address, and that's computed just by we have this helper function, but really it's just caching the permission and giving you a bytes32 permission ID. And the reason this is important is because we have this function on the policy, which is that non-transferable NFT contract, which checks the policyholder. Does the policyholder have the proper permission ID to create an action? And it might be helpful to now go into what exactly a permission ID is, and what's its relationship to the role. And so I can just do a quick overview here. As we covered, the policyholder, it can be an EOA, it could be a smart contract, it could be anything that could be represented as an Ethereum address. They hold this non-transferable ERC 721, and then the way policies, roles, and permissions relate to each other are policies have one to many roles, and roles have 0 to many permissions. And so you can think of roles. We have core developer and grants program reviewer and strategy creator here, and then permissions are this target selector strategy tuple that's used for action creation. And so maybe the core developer has some role where it allows them on the some proxy contract to call the upgrade function with the veto strategy. And so that's hashed and that's stored as a permission. And so that's how policyholders and roles and permissions relate to each other. We then go through, assuming the checks pass, we create the action, and we emit an event, and we begin the action process.
Yeah, Austin, question. Could you maybe go a little bit deeper into strategies? I'm still a bit confused by that. So what is
Yeah.
a concrete example of what a strategy is?
Yeah, so I think strategies are a great place to actually go through next. So strategies, there are these contracts that define the logic for think of for the action state transition. And so I'm going to make heavy use of these diagrams, but they when you think of what is an action and how does it go from active to executed, this is a good reference here where starting when so we just went through create action, the creator called create action, and so now this action is in the active state. Let's say it's we're transferring ERC20 tokens from our account. The um, the way, like the happy path for a an action is that there's an approval period where the strategy sets the rules for how the action is approved. So I'll go into the different strategies that we've launched Llama with. It's important to note that every instance is self-governed and self-managed and standalone. So you can create additional strategy logic contracts. But some of the strategy logic contracts we have are a relative voting strategy. So let's say the approval rules are that 51% of the core team role or the grants program reviewer role needs to approve a strategy. It could approval periods could use absolute numbers. So maybe you have a strategy that says two other developers need to approve a strategy, and that's gives you some context on how the approval process works. For the once an action is approved, then what happens? Well, then it's eligible to be queued. And once an action is queued, it goes through what's called a disapproval period. And so the disapproval period is if the approval period is, you can think of it as like for only voting, then the disapproval period is against only voting. And so what you do is set rules and a role for a disapproval period. And so this means you can maybe the community, maybe the token voting DAO, the token holders, it have the right to disapprove an action, or maybe that grants program example, grants program reviewers can disapprove an action, which, and maybe it's set so 20% or 2 or 5 or 10%. If they signal that they want to disapprove the action, then the queuing will fail, and the action won't be able to execute. If it passes the disapproval period without getting vetoed, then the action can be executed. And so the thing to remember is the approval period and the disapproval period are both optional. And so this is a really flexible system. So if you have both off, then basically an action can be instantly executed. As soon as it's created, it can be executed. If you have both on, then you have a vote and a veto. If you have just the approval period on, you have a vote that then can be executed after the vote. And if you have just the disapproval period, then you have an optimistic strategy where it automatically gets to this queuing period, and then it can be executed automatically after a set number of time, let's say 7 days, unless it's vetoed. And so really flexible in the different ways you can construct strategies, and I can actually get into what a simple strategy looks like.
Nice. Is the disapproval logic also embedded inside the strategy?
The So what's embedded inside the strategy is I can open up this interface so you can get a better sense. The core, like each strategy, according to this Llama strategy interface, encodes functions that the core can call for validating and checking how an action is proceeding through those state transitions. And so what's in this strategy is functions like check if disapproval is enabled, is an action cancellation validation strategy function, a function to see is an action active, is it approved, is it disapproved. And so we can walk through like what that actually looks like in a real strategy. So in this strategy I'm going through, it's called Llama relative quantity quorum strategy. And the really simple way to think about it is it allows you to set percentages based on a role. So that, 51% approval threshold or 70% or something like that. And what we can see here is actually, if we go to the, it inherits the relative strategy base. What we see here is that we can look and see the logic for, something like is action approved or is action disapproved. And so what it's checking is, to be clear, like these are functions that are only called by the core. And so by deploying strategies to having many strategies and deploying them to different contracts, what you're doing is like setting up this modular system where for any given action, for action number 82, the core can reference these functions and determine, is it active, is it approved, is it disapproved? And you can see, it's the logic it's using is, well, is it approved? The core passes in all the action info, and then the strategy, in this case, the strategy tells if it's approved by seeing if total approvals is greater than the get minimum amount needed. And in this case, get minimum amount needed, it's passing in the min approval percentage and the approval supply based on the action. And it's actually doing the calculation to see, okay, did 50% or more, of the approval role approve that action? And then if you want to see where in the core, like this is being referenced, you could see like we have an action state getter, and you can see the logic for how it determines for any given action, what state is it in. And it actually references the strategy to see, is the action active? Is it approved? Is it disapproved? And this function can just return, what state the action is in. Does that make a little more sense?
Yeah, let me try to summarize that, and please correct me if I'm wrong. So basically, I have a set of states, and the strategy defines how to get from one state to another.
Yes,
Okay, okay, then I get it.
exactly. And so you could see this, if we go to the enum here, you could see what the action states are.
Mm.
And the core knows about the action states, and it has the validation logic. So if we go to if you go back to the core, and I know I'm jumping around here a bit, but if you go to the the execute action function, then you could see that there are checks. There's a check here where the current state has to be. We use that get action state function, and the current state has to be queued, or else you can't execute the function. And so if you look at these action states, the core knows about that. But what the strategy does is determine, how do those state transitions pass. And so we just created our action. We can, so we're now in the approval period. And so I can go through what casting an approval looks like. And so if you look here, casting approval is another function that's being called on the core contract. And the way to think about how roles and permissions tie into these core contracts is when it comes to roles, they are used to determine who can cast approvals and cast disapprovals. And when it comes to permissions, they're used to determine who can create actions. So now that we're in the casting approval process, roles become a lot more important. And so what we see here is we have this approvals mapping on in our contract. So you can see in the core we have a mapping from the action ID to the policyholder to this Boolean, have they approved or disapproved. The reason this is important is to ensure that no one approves or disapproves twice. And you can actually see that in if we go back to this cast approval function, that's set to true. And in this precast assertions function, we check that isn't already true. And so if we look at these precast assertions, a lot of Llama's governance framework. So a lot of what Llama does is determine what is determine validation. What who's allowed to cast approvals or disapprovals or create actions, and how exactly does that work? And so in this precast assertion function, you could see a lot of that where it's you know is we're using this precast assertions for both approvals and disapprovals. And so you can see we're passing in the action info. We're passing in for this policyholder who's casting their approval for this role. And the active state is the expected state to be able to cast an approval. We can go in and check, okay, are we in the expected state? We have this Boolean here to see if it's an approval or a disapproval. We check that, okay, if you've already casted, you can't cast again. We have a checkpointing system to check whether you have a role and the quantity of a role at a previous timestamp. And so I can get into more how we use checkpointing. We've adapted it from Open Zeppelin's checkpoint library, but the basic idea is that you want to checkpoint, and this is something that's common in a lot of governance frameworks, is that you want to checkpoint at a previous block, so you avoid race conditions with if in the same block your roles are being changed or new policies are being issued. You want to have certainty that you're using a consistent state for all the action process. And so what happens is at action creation time, we're referencing a lot of these values around the policyholders and also around the current action state at a previous timestamp at block timestamp -1. And so I can get more into how that works as well. But first, going through the strategy here, and so you could see where we reference the strategy in these precast assertions. We're saying, is for this specific action, is approval enabled? We're getting their quantity, and so we're getting roles have a quantity attached to them, and so it allows you to do things like set, by default it's 1, so everyone's voting power is the same, but you can imagine wanting to have certain policyholders with a higher quantity, and so we're calling this get approval quantity at. So like at the checkpoint time, what was the this policyholder's quantity, and we're ensuring that's not 0. And if that passes, then we can be sure that we can continue on with the approval process. And so you can see we do the precast assertions, and then basically we go through, we set approvals to true, we calculate the new cast count, and then we have a check here if the approval actually passes. If this, let's say the threshold was 50%, and we have 6, the approval role is the grants program reviewer, and we have 6 of them. If you're actually the third policyholder casting, then we can automatically queue that action and transition it to the next state. And so that's a bit of a deep dive into how the action process works and how approvals are cast. I just wanted to go and show the action creation and how the checkpointing works a bit, but I'll pause there just in case you have any questions.
Yeah, and in the last function, create cast approval, just from a smart contract engineering point of view, I find it interesting that you emit in the middle of the function and not at the end of it. Does that have a specific reason? Line 689. Just out of interest. 89
Yeah.
there.
Yeah, for sure. Yeah, no specific reason other than the this logic that follows the is more just kind of a code organization thing, which I'm a
Okay.
fan of. If if the transaction reverts in this step, then it won't matter anyway. And so what we're doing is casting the approval when the approval should be cast, and then in this logic here, we're actually checking. Did this approval push this action over the edge into being in the approved state? And if it did, let's automatically queue it.
Okay. Okay. I think just doing the emit at the end would save some gas in case in a failure case, but makes sense.
That's true.
Okay.
Yeah, no,
Okay.
that makes sense. And this code right here is it shouldn't. I mean, it shouldn't fail. Something has gone very wrong if it has, because all it is doing is just checking the current state, and this is a getter function, and then it's just comparing it to approved and just calling queue action if it's
Famous
approved.
last
So
words, Austin. Famous last words.
yeah, right. Well, yeah, hopefully our test coverage and our three audits would have picked that up as possible. But we actually do that in another place too, where we have these checks that should never be called. The so if you look here, this is the initialization function. We make heavy use of minimal proxies. If you think about the architecture, so we actually use no upgradable proxies, but heavy use of minimal proxies because all these Llama instances, they have the same logic contracts, but different. They're configuring them with different parameters, and so you can see this. Kind of what we're doing here when we initially create our instance, we're creating the executor and initializing the policy and deploying the initial strategies and all that stuff. And then we have this check here too, that we have this concept of the bootstrap strategy, which is basically just like a check to make sure that you can't deploy a bricked instance. So we have this concept of like, okay, you need an initial strategy that works in a certain way. And so this actually should it's not possible for actually to have this thrown in production, but we just added this check, just in case, just to provide programmatic guarantees that the whole deploy will revert if this strategy is not authorized.
Okay. Okay.
Um,
So it's
that goes
basically like
into
a sanity check when deploying, basically.
Mhm.
Makes sense.
um, that goes into a lot of the actions. Some other things I wanted to cover were um, yeah, I'm just scrolling through the Llama Core contract first to see. Yeah, one more thing that might be just to complete that process might be to cover what's the next step of actions, and then I also wanted to get into Llama accounts, which is a cool feature of Llama that is we include as part of the framework this first class citizen, which are accounts. You can think of them as like on-chain token wallets. And so you as your core instance can deploy many of these for cold storage or for the DAO treasury or for a grants program, and you can permission them independently. So how are tokens transferred? How are ERC20s transferred and 1155s and 721s and native tokens and all that stuff. Um, but before we do that, the so when an action is approved, when you pass that approval threshold as specified in the strategy, and so if we go to just go back to the strategy and kind of go to get the to make the strategy logic like a little more clear. The When we're calling that get approval quantity at, when the approval is actually being cast, you can actually see that we're calling on the policy we're calling this get pass quantity, this like timestamp value, which is like, okay, at action, at this checkpoint time, the time the action was created -1, what was the policyholder's quantity. We can see, getting also the approval supply, how that looks. So you can kind of see where the checkpoints, fit in, and how we're checkpointing these values, and how the strategy is referencing that to determine the logic. The If we then get into the queuing of an action, which is what happens after the action is approved, we can see that the the queue action function does a few things here. Let me get into the public function first, because I think it would be good to see that. So queuing and executing actions are actually completely public functions. So we could run our own off-chain infrastructure to call these. A user can do the same. Really, anyone can do this. And some simple checks: are we in the right state to queue the action? And if those checks pass, then we can go ahead and queue the action. And the way we do that is by setting this this min execution time variable. And so all that does is it takes it references the strategy. How does the strategy calculate the min execution time? And it uses that that value. And the thing to know about what is min execution time, in this case, for like the strategies we created for this, we set the min execution time to be the block.timestamp plus the queuing period. And so all it's saying is after the queuing period, then the execution period begins. And so but we built things in a modular way. So theoretically, a new strategy could be created that specifies a different min execution time. And so if we go here to this queue action function, you can see we're specifying the min execution time. And the reason that actually changes the state is if we go to get action state, there is this check that is the min execution time defaults to 0. And so once it's set, it's not 0. And so that will cause this get action state function to return action state queued. And then finally, on the action process, the execute action, also a public function. This is the kind of crux of where all the voting and vetoing and approval periods and disapproval periods, all that passes, and now it's time to execute the action. And so when that's called, again, a lot of these checks, okay, have we passed the min execution time? We're now in the execution period. Is the action in the current state? We then set action executed to true, just to follow good checks effects interaction pattern. We then go ahead and execute the action. And so when you see we pass in all the parameters of the actions info, and we can see how simple this Llama executor contract is. The reason we created this separate contract is just because we support delegate calls as well. And so just to provide an additional safety layer, we don't want, of course, we would expect instances not to permission malicious contracts, but just in case, if it would be dangerous if the core was calling directly, because then a delegate call could overwrite storage in the core contract. Instead, we use this executor contract, which has no storage, and all it has is a simple execute function that could only be called by the Llama core. And all it does is it checks if it's a script, and scripts in the Llama system are defined as contracts that can be delegate called. So that makes them really handy to do, common governance actions that you want to automate or provide an additional layer of abstraction over. So maybe you're some lending protocol and you have a risk script that has some function that updates multiple risk parameters in some way, and because the Llama executor is the owner of your risk functions on your protocol, then by delegate calling the script, it can execute that code and do it in the context of the protocol's owner. Um, and if it's not a script, then it just calls with the passed in data. And so that is the crux of how the action flow works.
Okay. Min execution time still confuses me a little bit. So you have min execution time to avoid some malicious execution where, for security reasons, you cannot do something in the same block, or why exactly do you have that?
Yeah, the concept of min execution time is just the uh, the way to think about it is min execution can't be calculated at action creation time. So you have a concept of like at some timestamp, an action is eligible to be executed, right? It's the reason it's not necessarily known at action creation time is because if you think of these approval periods and disapproval periods, so active to approved is the approval period, queued to executed is the disapproval period. They could potentially be a variable length, specifically the approval period. And so you can have an approval, you can have a fixed length approval period. So maybe it's fixed to 7 days, or you can have a non-fixed length approval period. So as soon as you meet the necessary approvals, you're ready to be queued. And so if you don't, because of that, you don't actually know when the action is ready to be executed until it's queued. And so until you call the queue action function, you can't set the min execution time. And so then once it's set, then we know the action is in the queued state, and we have the time that we can then check against for the execute action function to ensure that the min execution time has passed before an action can be executed.
Hmm. Okay, okay. I see. So basically, it's like a time buffer to make sure votes, for example, come in or something. Okay.
Yeah, to make sure that the yeah, that it's more to make sure that the queuing period has passed. And so if we look at how it's implemented, we can see um, this is being called again, these functions that the strategy exposes are meant to only be exposed, only to be called by the Llama core. And so the Llama core only calls this function when the action's being queued. So that's like the block dot timestamp of the action being queued. You add in the queuing period, which, let's say it's 7 days. Um, and so then we know the min execution time, the starting point for when an action can be executed, is in 7 days from now, and now being when the action is queued. And so if we didn't have this check, then we wouldn't have a way to ensure that an action is only being executed when it's the queuing period has actually passed.
Okay.
Um, yeah, so yeah, I know this is there's a lot of concepts here, and especially a lot of this, if you think of a lot of the existing governance frameworks, a lot of these best practices have been adapted in Llama, and I actually think it's a very cool. It's actually a great way for Solidity developers to initially learn. If you think about diving into maybe a DeFi protocol, it's there might be some math required, there might be some financial markets knowledge you need. Governance is has a lot of interesting logic that's actually easier, I'd say, to understand for let's say a developer who's new to the space and just getting into smart contracts. And so there's a lot of these code bases that are really fun to look at. I just pulled up I wanted to show the Llama policy contract. The Llama policy contract is this non-transferable NFT contract, and I wanted to show how this looks. And so the for the way this works, we talked about role management and we talked about permission management. Um, the You can actually see, kind of how, the policy can, roles can be set and permissions can be set, and these some of these like getter functions work. And so if we go into maybe a good place to start is to actually go over the uh, just we can start simple and get more complex, but so actually when when the core is checking, hey, does this policyholder have this role? What it's doing is we have this checkpointing system set up so we could see, at the latest checkpoint, is the quantity of your role greater than zero, and return a boolean. An interesting thing to mention as well, similar logic applies to having a permission ID. A similar thing, an interesting thing to mention is just how you can use your Llama instance to govern over your protocol contracts. It's also what you use to govern over Llama itself. So when you think of a question of like, let's say you want to give a grant a new permission to a role. The question is who has permission to do that. Well, the way you do that is by using your Llama instance. So maybe you have like an operations team, or maybe token holders can do this, but you set up the permissions. So you define both a strategy and who has the permission to propose that action. So maybe it's the operations team can propose setting a new permission for a role, and the strategy by which it does that is you need an 80% buy-in from the other operations team members. And so if you look at the set role permission function, we can see we're passing in the role. This permission data struct is just that tuple, which is the target contract, the function selector, and the strategy. And then we have this like Boolean, are we adding or removing a permission? And then we can actually go and see and check, is the role already assigned? We can calculate the permission ID from the permission data. We have this can create action struct or mapping that where we set the permission, and then we emit the event. And so you can see in this mapping, we're mapping from the role to the permission ID to a Boolean if it has a permission or not. And so that gives you a sense of just some of the things that the Llama policy can do.
Nice. Should we maybe take a look at, you wanted to show us the accounts, or I forgot what you called that, the accounts, right?
Yeah, that'd be a good thing to dive into too. So what we've gone over today is the core structure so far is the core structure of a governance framework, right? How are actions created? How does the validation work to determine who can create actions? How are how does the approval process work? How does the disapproval process work? What are the roles for who can approve and disapprove? And then how are actions ultimately queued and executed, and result in some on-chain transaction that does take some action on behalf of a protocol's governance. The and the key things to note there are that the roles and permissions are encoded in this Llama policy. The strategies are encoded in these separate contracts, and that the Llama the core the governance, in addition to governing over external protocol contracts, can govern over itself. So it can add new roles, remove roles, add permissions, remove permissions, create new strategies, and take part in that whole process. Another thing it can do is create accounts. And so if we look here, we have a Llama account, and a Llama account is a simple contract that you could basically send funds to, and then use your Llama governance to manage them. And so if we look at some of the basic functions here, maybe something like a transfer ERC20 function, we can see that it's protected as in all contracts that are Llama governed is protected by this only Llama modifier, which checks that the message sender is the Llama executor. And then, assuming that check passes, then it just does a safe transfer based on the provided data. So you provide the recipient and the amount and the token, as we can see in this struct here. And we can, we can permission this like any other function. And so we can receive, it's permissionless to send tokens to the account, but then to transfer and approve outgoing native tokens in ERC20s and 721s and 1155s. That's all permissioned by Llama. And so that's another cool feature that you can optionally use if you're using Llama for your protocol's governance.
Nice. Nice. Really cool stuff. Cool, Austin. We are 5 minutes away from 1 hour, so great timing. Maybe just the contracts are audited already, right?
Yeah, they've been
Uh,
audited 3 times.
nice, nice. How far away are you from fully launching this? Because I'm currently on your website and it says get a demo, so I think there's still front end, back end stuff happening.
Yeah, so we're exactly where we are today. Is And I just wanted to show that that checkpointing system. So we have these two checkpoints, and then I would love to talk more about where we're at. We have this policyholder checkpoint that and you can think of this as like a role supply checkpoint. And so what this does, it's adapted from OpenZeppelin's checkpoint library, and it's pretty lightly modified. But all it does is it's really cool code to analyze. You can see some like on-chain binary search happening here. But basically, all you're doing is at any given timestamp in our supply checkpoint for a given role, based on a timestamp, what is the number of holders and what is the total quantity of that role, and then for our policyholder checkpoint, what is the quantity of that policyholder's role, and what is the expiration date of that policy. And so what that allows you to do is we make great use of this in our policy contract, which the core references for getting these snapshots of time. And so you can see based on a token ID, based on a sender's and addresses policy, you can and given a role that they have, you could see how we snapshotted that policyholder's role. And so you can then reference this mapping into doing things like getting the current quantity, but also getting a past quantity as well. And so we do that both for a role for the policyholder using the policyholder checkpoints, and then for a role supply as well. So we can actually see the supply of the role. And the reason this is important to be able to say at a given timestamp, what is the supply of a role? Because what it allows us to do is actually when we create an action and lock in that timestamp. So for every action that's being created, we lock in the time. We snapshot the data at that point, so it can't change while the action process is going on. And we could say what is for the core developer role, what is the total supply? And so if you have it set so 50% need to approve, then we can have that calculated at a specific timestamp. And so just wanted to show that. In terms of like where we're at, Llama is deployed to most major EVM chains. We've been audited 3 times. You can actually see the addresses here. You could see the factory contract. We are in the process. We haven't publicly launched because we're in the process of onboarding our initial customers right now, and we want to launch. We think it's more fun to launch with a group of customers and actually show when we get really public about what we're doing, actually show how Llama is being used. And so it makes it easier to handle the whole public onboarding at once when we have case studies to reference. And so yeah, we're open to any conversations. We have the off chain application as well. We can show you a demo. We can customize a demo specific to your protocol, and we can kind of get into we're ready to bring you on board. So yeah, if you're building any sort of protocol or on chain organization that has some form of privileged access, we'd love to talk and share our experience.
Awesome, Austin. This was a lot of fun. Thank you very much, dude. And yeah, I'm gonna link, so it's llama.xyz. I'm gonna link the GitHub as well. Best place to reach out to you personally is probably Twitter, right? So I'm gonna link that too in the
Yeah, just
description.
Twitter.
Awesome. Austin, this was a lot of fun, dude. Thank you very much.
Thank you for having me.
Awesome, guys. See you in the next one. Bye bye.
Bye.